In the Chem Activity number 14 and the corresponding videos, we'll explore the concept of ideal gases and the ideal gas law. To begin, let us look at a cartoon that represents a teacher inquiring of his students who knows what an ideal gas is like. And you can see that such a question can conjure all kinds of ideas. The word ideal is used in everyday English, and therefore many meanings can be associated with it. In chemistry, however, we have a very specific idea of what ideal gas means, a very specific kind of definition. Rather than give you the definition right here, I'd like to unpack the idea of what we mean by the ideal gas by talking you through a number of examples in this video and in others. In the end, you will, I think, have a clear sense of what we mean by ideal gas. Here in teaching model number 1, I'd like to talk you through the submicroscopic view of argon in its 3 states of matter. So in a sense, what we're doing here is visiting the kinetic molecular theory of matter, and will include solids and liquids as a contrast to the properties of gases. Recall that all matter essentially can exist in solid, liquid, and gaseous phases. So while we normally think of argon in its noble gas character as being a gas, it's only a gas at 1 atmosphere pressure and above 87.3 Kelvin. So let's look at a little simulation that helps us think about this, and then we'll come back to these notes. So here I have a molecular representation of argon at a temperature of around 36 Kelvin. Now those blue dashed lines that you see are representing the intermolecular forces that are holding the argon particles together. I'd like you to notice the sort of motion that the atoms are engaged in. It's essentially a vibration. Notice that the atoms do not flow over one another, but rather they're fixed in position. So really the motion is vibrational. Now, this particular bunch of argon atoms is floating all over the place. Normally, solid argon would be drawn down to the bottom of the container based on gravity. One of the other things that I'd like you to take note is when we think about what defines the volume of a solid, well, essentially, I hope you can appreciate that it's the size that the particles themselves take up. And further, what would define the shape of a solid would be the actual shape of the atoms themselves. So what I'm going to try to do in this simulation is now increase the temperature so that we can see how that affects our model and the particle motion here. So at first I'm just going to increase the temperature to, let's say, around 60 Kelvin. And perhaps you notice that with that increase in temperature, the vibration has changed. The vibration has gotten a little faster. The distance between the particles is a little greater. So indeed, the density of a solid can change with increasing temperature, although usually that's quite a minor change. And my intention now is to get to a temperature somewhere just above 83 Kelvin. So the temperature that we now have is just around 83 Kelvin. I hope you notice that the particles now, instead of being fixed in position relative to one another, actually flow over one another. And this is consistent with what we know about the liquid state. The particles in liquid states flow over one another, and therefore at the macroscopic level, the liquids actually flow. So you know you can pour water out of a container, but you can't pour ice out of the container in the same way. Solid ice does not flow. Liquid water will flow. And the reason why it flows has something to do with what's happening at the submicroscopic level. The particles themselves can flow over one another. There are still intermolecular forces that are attracting the atoms together. In this case, of course, we're dealing with argon. But overall, the particles do not have enough energy to break away from one another. If we think about what defines the volume of a liquid, I hope you can see that it is essentially still the space that the particles themselves take up. If we think, however, what defines the shape of a liquid, in this case, it actually depends on what kind of container we put the liquid in. So imagine that you have 100 mils of water in a beaker versus a graduated cylinder versus a large volumetric pipette. It would be the same volume, but there'd be a very different shape. So the next stage in this simulation is to increase the temperature even further. So now we're at roughly 400 Kelvin. At this temperature, I think you can see that the particles have enough average kinetic energy that now they've essentially broken away from one another. We say for the most part they have broken the intermolecular forces. The sort of motion in this case, instead of just being vibrational and instead of just rolling over one another, is that we have real translational motion across the screen. So essentially the particles will fill the entire volume of the container. It's a random chaotic motion. The particles are also rolling relative to one another, and to some degree they would still be vibrating. So there's all kinds of random chaotic motion. Now the temperature here is roughly 400 Kelvin. If I increase the temperature, I'd like you to take note that things do change. It's still the random chaotic motion, but now the particles have a greater average kinetic energy, so therefore they are in fact moving more quickly throughout the entire container. One of the other things that you may notice, however, is that not all the particles are moving at the exact same speed. So while there may be a certain average kinetic energy, some particles are moving slowly, some medium speed, and then of course some are moving quite quickly. So again, not all the particles have exactly the same speed. So with that little bit of introduction, let's go back to our notes. So let us summarize some of the things that we've just seen. So for one, if we want to talk about the volume of a solid, it is essentially determined by how many atoms you have and their relative arrangement. Further, if you want to talk about the shape, it is essentially how the atoms themselves are arranged. So if you think about the shape of your calculator or the coffee cup or the table that you might be having your computer resting on right now, all of those have a defined shape because of the atom arrangement. We saw at the submicroscopic level that the type of motion that's occurring is vibrational. So I've made a little sketch of a group of atoms, presumably argon, in the solid state, and in this case they are at the bottom of the container. But do imagine that they're arranged in a very defined way, and that they're all vibrating, and they're fixed in position relative to one another. If we increase the temperature, however, to around 83.8 Kelvin, up to about 87.3 Kelvin, argon is in the liquid state. So picture that all of those round balls represented in the diagram are now flowing over one another. So there's still the vibrational motion, but now there's a flowing motion. It is true that the volume of a liquid is still defined by the atom number and the arrangement of those atoms. The shape, however, will be the shape of the container in which the liquid finds itself. Finally, the type of motion will be this flowing. This flowing includes a certain amount of vibrational motion and a certain amount of translational, but there still is a relatively strong attraction between the particles relative to the amount of average kinetic energy that the particles have. At temperatures above the boiling point, in this case 87.3 Kelvin, then the volume of those particles will be defined by the volume of the container. In other words, the particles are now in the gaseous state. The shape is defined by the shape of the container itself. And of course, the type of motion, as we saw, is a random chaotic motion. There's a translational motion, There's a vibrational motion, there's a rotation motion. All of these things are happening. Now in the box in your diagram, I haven't filled in the particles. You could do that, fill them in. You would show them filling the entire volume of the container. It's a little hard to show motion with static particles, but we could show arrows in different directions to show that these things are moving. Understand that each particle would have its own kinetic energy and its own speed. While there'd be an average kinetic energy and an average speed, as I say, each particle has its independent type of properties. Here are some important conclusions that I'm hoping that you're taking from these observations. For one, you saw that as we increase the temperature, the particles themselves started to move more quickly. That motion and that speed of the motion is related to the average kinetic energy. So we can say here that the temperature is related to the average kinetic energy of the particles. And in fact, the only way we can change the average kinetic energy of particles is to change the temperature. This will be an important point as we make our way through this unit on gases. The next point that I hope you noticed is that in contrast to solid and liquid states, in the gaseous states, the particles have enough kinetic energy to break those forces of attraction. I refer to them as intermolecular forces, and towards the end of this semester, we will spend some time looking more specifically at the nature of these intermolecular forces. Because the total volume of a gas is determined by the size of the container, another unique property of gases relative to liquids and solids is that gases can be compressed. There's space between the particles. And in fact, one of the things that we'll be emphasizing is relative to the actual size of the particle, there's a huge amount of space between each particle. So gases can be compressed.